Bismillahirrahmanirrahim. Now our next theorem, that linear transformation for the same dimensional vector space. Let U and V are n-dimensional vector space over the same field F. A the set A consists the elements u1, u2, un, and the set B consists the element v1, v2, vn are the basis of the vector space u and the vector space v respectively. Then there exists a unique linear transformation T from the vector space u to the vector space v such that TUIs is equal to VIs I 1 to up to n, that is TU1 is equal to V1, TU2 is equal to V2 up to so on. TUN is equal to VN, where UIs are the element of the basis of the vector space U, and VIs are the element of the basis of the vector space V over the field F. Proof. Suppose that set A contains the element u1, u2, un is the basis of the vector space U. So any element u of the vector space U over the field F can be written as a linear combination of the element of its basis vectors a1 u1 plus a2 u2 up to so on an un, where a1 a2 up to an are the element of the field. We define a mapping T as Tu is equal to T a1 u1 plus a2 u2 plus up to so on an un, that is T T summation of the element of the basis vector. And this can also be written as a1 tu1 plus a2 tu2 plus up to so on plus an tun, that is summation ai's tui's I1 up to n. And the T is a mapping according to the given condition that tu1 is equal to v1, tu2 is equal to v2, tu3 is equal to v3, and so on. Tun is equal to vn. Therefore tun is equal to vn, that is summation I1 up to n ai's vi's I1 up to n. To show that T is a linear transformation for any two element xy in the field in the vector space U, alpha beta are the element of the field, then the linear combination alpha x gamma beta y is an element of the vector space U over the field F, and the element x can be written as a linear combination of its basis vectors, that is b1 u1 plus b2 u2 up to so on bn un, that is summation I1 up to n bi's ui's. And y can also be written as a linear combination of its basis vector, that is y is equal to c1 u1 plus c2 u2 plus up to so on plus cn un, that is summation ci's ui's I1 up to n. And where b1 up to bn, c1 up to cn are the element of the field. Now apply the operator T on the linear combination of x and y we have, which is an element of U. T alpha x gamma beta y is equal to T, and alpha x is equal to summation alpha multiplied by x is equal to summation bi's ui's I1 up to n plus beta, and y is equal to summation ci ui I1 up to n, that is t. And we can rearrange this equation we have, that is ui is common in these two terms. We have summation I1 up to n alpha bi's plus beta ci's, where I1 up to n, and according to the given condition, according to this condition, summation I1 up to summation I1 up to n ai's ui's can be written in the form of summation I1 up to n ai's tui's. Therefore, according to this condition, we can rewrite this strip according to this condition, that summation I1 up to n, the constant alpha beta i's gamma beta c i's I1 up to n tui according to this condition, and each tui is gives a vector vi's according to this condition, that is summation I1 up to n ai is a constant in a previous step, and in this these steps alpha beta i's gamma beta c i's are constant, and t ui is equal to vi's according to our these steps. According to these steps, that is, after the rearrangement of these steps, we have uh, alpha summation bi uvi plus plus beta summation civi, and which can be rewrite as alpha summation I1 up to n bi tui, that is each ui is equal to vi. Therefore, we replace vi by tui plus beta summation I1 up to nci tui, and according to our previous step, we have alpha multiplied by t summation I1 up to n bi ui plus beta t summation I1 up to n ciui, that is t is a transformation, that is the summation of biui gives an element x of the vector space u, and the summation ciui gives an element y of the vector space u, which is equal to alpha tx gamma beta ty. There, that is t is a linear transformation from the vector space u to the vector space v over the field f.